Okay, so let's take a look at chemical bonding. This is page 11 of the lecture outline book. Just recall from page 3, back when we did the first video of the semester, we took a look at some organizational details about life, and we started out with the cell and went backwards and went forwards, and we said that eventually we're going to have to talk about chemistry. We're going to have to talk about molecules like proteins and carbohydrates and things like that. But to talk about those, we need to talk about atoms, which was what we've been doing, which is what we did the first week of the semester, because it's these that comprise those. The question for today is, how do you attach atoms to each other to form molecules? How can I take atoms of carbon and oxygen and nitrogen and hydrogen and put them together to build a big complicated molecule, such as a protein, for example? So we're going to start to take a look at that today in this video. One type of chemical bond, and the answer to that question, how do you put them together, is chemical bonding. There's different kinds of chemical bonds. One type of chemical bond is called an ionic bond. And to understand the ionic bond, you need to go back to what we did pretty recently. We talked about ions. So let's do a quick review of that. You've drawn a bunch of atoms already, and then we talked about how they might ionize. Just as a refresher here, let's discuss lithium. Lithium is one that you've drawn already. We said it has 3 protons, 4 neutrons in its nucleus, and it has, therefore, 3 electrons. That's a lithium atom. It's got 1, 2, 3 electrons. 1 valence electron. And we said the fact that it has only 1 valence electron makes it unhappy or uncomfortable. And why is that true? Here's a general statement. You have to recall what you already know, that atoms are not happy, they're not stable, if you will, unless they have full valence shells. And most atoms don't have full valence shells, except for a handful of them. They either have extra electrons or they're missing electrons, however you want to look at that. So this idea, this concept that you see right here is going to be foundational to our discussion of bonding. So again, go back and look at lithium and say, gee, that lithium is not pleased with that one stray valence electron that's sitting there in a shell that could be holding 8 electrons. It's annoyed by that one particular electron. So what lithium will typically do in real life is it will discard or throw away that one electron and become a lithium ion. In this case, it'll become a cation, a 1 positive ion, because it threw away a negative electron. There goes that electron. So what do you have as a result of that? Well, that shell doesn't exist anymore. You default to the previous shell. You got a full valence shell. You're a stable lithium ion. You just happen to have more protons than you have electrons, so you have the plus sign there. This is a review of what we did with ions. If this is not clear, please go back and look at video 6 from week 1. It's the ions video. Another quick review. Let's take a look at the atom fluorine. If you're fluorine, you're also not happy and you're also unstable because you've got 7 valence electrons and you could have 8. You really, really, really want to get one more and fill in that last slot so you have the complete valence shell. So let's say you could do that. Let's say you could acquire an electron from somewhere. We're not describing where yet, but we will. Let's say you could acquire an electron from somewhere. Go ahead and do that. You're going to have now 1 more electron than you have protons. Let's say that's that new electron that you just imported right there. You got a full valence shell. You're happy. You're stable. That's great. But you have more electrons than you have protons. You got 10 electrons. You got 9 protons. You're going to have a negative charge on there. We'll call that a fluoride ion. It's an anion, a negative ion, and that's a form of an ionization. So again, please be sure that you're clear on how ions form. We did that last week. This was just a quick review because it's a good lead-in to the discussion of ionic bonding. So again, back to page 11 here. Let's say that the 2 events that we just highlighted are going to happen in the same place at the same time. I'm going to use that lithium and that fluorine as an example. I'm going to show you a different way to draw these atoms, though. For example, let's say I wanted to draw a lithium atom more easily. In other words, let's say instead of drawing it out in all of the detail that I did earlier, maybe I only want to know what its valence electrons look like. Remember, that's an important thing to know. So maybe instead of drawing a lithium atom with 1, 2, 3 valence electrons, etc., maybe I could just do this. I'll draw a lithium atom like that. It's lithium, so I can look up how many protons and neutrons it has if I wanted, and I put that one dot out there. That one dot indicates the one valence electron that lithium has. Similarly, for fluorine, before it's a fluoride ion, it's got 7 valence electrons. What if I do this? I'm going to go 1, 2, 3, 4, 5, 6, 7. What you see there is the symbol for fluorine, and you see the electrons represented as dots found in the valence shell, just the valence electrons. What you see here and here are examples of what we call the Lewis dot structure for these particular atoms. This is Lewis, a chemist that this was named after. This is a very common way to draw out atoms. Sometimes you want to know all that detail. Sometimes all you want to know is the atom that you're dealing with and where the valence electrons are. Remember how important valence electrons are? We've stressed that already. We're going to stress it again. So if that's all you want to know, maybe you could draw it out like that. It's common for chemists to use Lewis dot structures. We're going to use them in this discussion and going forward. That's why I'm introducing it right now in the middle of this video. Okay, so again, chemical symbol, draw the valence electrons around there. Don't draw the other electrons in the other shells. Don't tell me how many protons and neutrons are in there. Just draw the valence electrons. You got the Lewis dot structure. So let's kind of rethink what we've got already. You know what happens to lithium when it wants to stabilize itself. You know what happens to fluorine when it wants to stabilize itself. What if those two things happened very close to each other? What if those two events happened in the same vicinity? Lithium is going to give away its valence electron and become a lithium ion, and fluorine is going to gain an electron, let's say that one for argument's sake, and is going to become a fluoride ion. If that happens, what do you think these two ions are going to do? They're oppositely charged. Of course they're going to attract each other because oppositely charged objects attract each other. So if this and this happen in the same vicinity, in the same general space as each other, you're going to wind up with two oppositely charged ions. They're going to stick to each other. They're going to want to stick to each other. And you're going to wind up with, let's do a little arrow here, you're going to wind up with a new substance. We'll call it lithium fluoride, and we're going to write it out like that. So this, lithium fluoride, is a new substance. We're going to call it an ionic compound. You may see the word molecule used a little loosely to refer to this. It's a couple of ions that stuck to each other. Where those ions come from, they used to be atoms that ionized. So if all of this and all of this happens at the same place at more or less the same time, you're going to get this new compound. You took what was a lithium atom and a fluorine atom, and through a chemical reaction, you wound up with a new substance. That's a chemical reaction. You start with some stuff and you wind up with different stuff. So this compound, this new substance, has completely different properties than either this or this or this or this used to. And it's a standalone new substance, as I said, and we'll call it lithium fluoride. Notice that I wrote the lithium first and then the fluorine. I wrote that symbol, then this symbol. By convention, and you need to do it this way so it makes sense, when you write the formula for an ionic compound, you're always going to write what used to be the positive ion first and what used to be the negative ion second. You would never write that to indicate lithium fluoride. That doesn't mean anything in chemistry and is incorrect if you write that on an exam. That is lithium fluoride. Okay, notice that for every one lithium, you had one fluoride ion. That's implied when I write this symbol and that symbol. If that ratio were not 1-to-1, I would have to start putting numbers in here, and we're going to take a look at that briefly. But for the moment, I just want to relate this to the term that's on page 11, which is the whole point of doing this video, the term ionic bonding. So what we just did is illustrate how an ionic bond forms. You get an ionization to form a positive ion, you get an ionization to form a negative ion, and then the two oppositely charged ions stick to each other, because that's what oppositely charged things do. So one description of an ionic bond might be something like this. We'll call it the electrostatic attraction between two oppositely charged ions. Or between a cation and an anion, if you prefer to say it that way. What do I mean by electrostatic attraction? When you talk about electrostatic, you're talking about the charge on something, the electrostatic nature of the thing. So when we say electrostatic attraction, that's just a phrase that means oppositely charged things attract. So it's another way of saying this, it's the force that exists between the cation and the anion such that they come together and form a new substance that has new properties and new behaviors compared with the original parts. So this is an ionic bond that exists from here to here. And we've got a new substance as a result. So again, this is a legitimate chemical reaction. When you start with some stuff and end up with different chemical stuff, you've done a chemical reaction. In this case, somebody lost an electron to become that way, somebody gained an electron to become that way, and then the two pieces stuck together. So electrons are clearly involved in chemical bonding, certainly in ionic bonding. You see an example right here. In the next video, we're going to take a look at some other examples of this, but this one was just an introduction to what ionic bonds are, plus that little bit of reminder that we did, and that little bit of Lewis dot. I know we didn't use that yet, but we're going to need that in future videos. And before we start chemical bonding, I wanted to be sure you got that out of the way. So that's the take-home messages from this video. Please see the next video for a continuation of a discussion of ionic bonds and ionic compounds.